The idea of this little session is to apply what we talked about in the last two sessions in terms of electromagnetic induction into the whole idea of an AC, an alternating current generator. The main idea is what happens if we force a motor to turn by providing a force instead of getting an electric current to turn it. So if you imagine a motor that you might have built in the lesson, if you now don't connect that to a power supply but you turn it yourself and instead connect the cables to it to an ammeter, a sensitive ammeter, I wonder what would happen. This is the idea of today. So a little bit of a summary of where we're at from the last two lessons. We've covered quite a lot. We know that an EMF is induced when there is a change in the magnetic flux linking a conductor. This is not on the formula sheet, but it's worth thinking about this equation that the induced EMF is BA divided by delta T. B is the flux density, A is the area that flux density covers. So the quantity BA we call the magnetic flux. So this is the rate of change of flux, okay? We then had this idea of flux linkage, and this is the amount of flux that links through a coil with N turns of a particular area. So the complete formula is this one at the bottom, which is the induced EMF is equal to the rate of change of flux linkage, where N delta phi is the flux linkage through a coil. And remember, flux linkage is N phi, which is basically NBA, so a coil with an area with a magnetic flux density going through that area with N turns on the coil. Okay, so the AC generator, it's essentially the same as a motor. Mechanical energy is converted into electrical energy. The motor is the other way around, if you think through that. The motor construction, the commutator is used in the design. The slip ring commutator gives you AC. The split ring commutator will give you DC. That's sort of beyond the scheme, but if you're doing some extra reading, you might read about those. When spun, if you imagine this coil of wire here, when this is turned, the flux linkage, imagine this was a north pole and this was a south pole, you've got lines of magnetic flux going across. If this is turned, the flux linkage in that coil will change. So if we just put some lines on here, if you imagine these are the lines of flux, so these are your magnetic field lines from north to south, not particularly straight, but I'm sure you get the idea. So that would be the north and this would be the south. If you imagine as this bit in the middle turns, you can see at the moment there's the flux linkage through that coil is zero, but as it starts to turn, it's going to change. So how can we increase this rate of change? Because remember, flux linkage is a changing flux linkage will induce an EMF. Well, if we put more turns, so we can have more turns on the coil, or we could use a larger cross-sectional area, that would give us a greater change of flux linkage. We could use more powerful magnets, stronger magnets, would give us some more flux, a more greater change of flux linkage, or we could increase the frequency of rotation. The faster the frequency of rotation, then obviously the more the flux linkage is changing. This screen really is the very basics of what you need to understand about the generator. So if some of the other stuff gets a little bit complicated, come back to this screen. So we'll start the more in-depth analysis. We need to bring in some concepts within circular motion. This is motor. Now you can't see here on this particular slide and on the others, you can't see the three-dimensional view. So if we just we'll put some lines on here. This wire, if you imagine, is going to sort of be in that shape. This is what this would look like in 3 dimensions. So this sort of goes into the screen. So the wire will go all the way around this, like in that fashion. If I just change back to the pointer, you'll see it. All the way around in this fashion, the wire will go around this coil, but you can only see the end face of it. So this coil spins clockwise if it starts vertically in a magnetic field with angular velocity omega. Remember the definition of what angular speed is. The angular speed or angular velocity is the angle turned through divided by the time taken. Now we often talk about for one period, for one time period t, we know that the angular speed will be 2 pi over t, because the angle turned through in radians is 2 pi and the time taken is t. Rearranging that, we easily get omega equals 2 pi f, because f is 1 over t, and this is measured in radians per second. So this little t is the amount of time we let it spin for. If we let this particular coil spin at a steady frequency f, the total angle it turns through in radians will be 2 pi f multiplied by the time. This is basically a speed, omega, times time, in the same way that distance equals speed times time. So as the coil spins, flux linkage changes continuously. If we consider a normal line to the coil at an angle theta to the field line. So here's the coil of wire, and we've got this normal line passing through the centre. It's here. This is what we mean by a normal line to the coil, and it's at an angle theta to the field line. So if you imagine the field lines are passing directly across here, then this angle theta is literally what the angle is from that normal line to the field lines. So we know from last lesson that the flux linkage in the coil, when the normal to the coil is at an angle theta, is given by this equation that n phi for flux linkage equals BAN cos theta. And it's a maximum when theta is 0. So if you turn this coil, so instead of going in that plane, it goes vertically down the page, that is when the flux linkage in coil is at a maximum. Here's a little picture of what I mean. It's when it's at this point we know it's at a maximum, because you can see that in this orientation there are the most possible field lines going through the coil. So the flux linkage, if we replace theta in that formula by 2 pi ft, the flux linkage becomes n phi, which is flux linkage, and that becomes BAN cos 2 pi ft. So this changes with time t, and as shown in the next diagram, this is going to look like a cosine curve. So here we go, this is the cosine curve. We can see that the maximum value of flux linkage is BAN. The minimum value is minus BAN, and it's changing in terms of a cosine curve. There's a lot you can read from this graph. If you think of what the motor looks like when it's spinning, remember it's starting vertically up. Here we can see vertically upwards, maximum flux linkage. When it's gone through 90 degrees, minimum flux linkage. When it's turned all the way around through 180 degrees, maximum flux linkage in the negative direction. It's turned through 270 degrees, then it's flat again, minimum flux linkage, all the way back to a maximum. So we say that the induced EMF is 0 when the sides of the coil, which are into the picture, move parallel to the field. So when the sides of the coil that you can't see, when they're moving parallel to the field, then they're not really cutting through any lines of flux. If you imagine this turning, it's cutting through the most lines of flux here. And here it's cutting through lots of lines of flux as it turns. Whereas when it's at the top, it's not really cutting through many lines of flux. So the flux linkage is changing the most here and here. So if we look at a graph of our induced EMF, we can see the flux linkage changes the most here. So our induced EMF is at a maximum here, and also here. So our induced EMF is at a maximum here as well. Whereas in this position and this position, even though the flux linkage is the greatest, it's changing the least, so the EMF is the smallest. Remember that EMF is the rate of change of flux linkage. So we've gone through this thing, when is flux linkage at a maximum minimum, and when is EMF at a max and a minimum. Some extra notes on this idea of flux linkage. Two arguments for two ways of describing the same thing. Flux cutting, you can see when the coil's in this position, the induced EMF is a minimum when the sides into the diagram do not cut any field lines, and this is when the normal to the coil is at 0 or 180 degrees. So you can see there's no angle between a normal and the field lines. So this is where our EMF is going to be at a minimum. In terms of the flux linkage, this is when the flux linkage, it is at a maximum, but it's changing the least. So again, our EMF is at a minimum. Flux cutting, it's not cutting any, EMF is a minimum. Flux linkage, it's at its maximum, but it's not changing. So EMF is the rate of change of flux linkage, so minimum EMF. If we put the coil in the other position and just talk about the two arguments, flux cutting, this is cutting the most lines of flux, you can see. So this is going to be EMF at a maximum. But in terms of the flux linkage, this is where the flux linkage is at a minimum, but it is changing the most. As this turns, if this goes from 90 degrees to 95, 100, 110 degrees, the flux linkage changes the most rapidly. It goes from 0 and it increases at the most rate, at the highest rate. Okay, if we look at the two graphs again, we've got, this is our cosine graph, so this is the flux linkage equals BAN cos theta, and what we've talked about is the EMF is the rate of change of the flux linkage. Now that is the gradient of this graph. So if we did the gradient of this graph, if you do maths, you should think that the gradient of this graph, the gradient of a cosine graph, is a minus sine. So the fact that I've just drawn a sine curve might confuse you, but we will come back to that in a second. So the gradient of this graph is the change in flux linkage per second. This represents induced EMF. So this is the rate of change of flux linkage. So I know that at the moment then the gradient of this graph should be a minus sign, but I will come back to that. Just look at this formula just for a second, because I'm going to do the differentiation on this in one moment. This is the formula that we've talked about, that the rate of change of flux linkage is BAN cos theta. Just replacing the theta with BAN cos 2 pi ft, and then we know that omega equals 2 pi f. So we've got a formula here that we're going to integrate, which is, we're going to differentiate, sorry, which is n phi flux linkage equals BAN cos omega t. This is the equation for the induced EMF. Now this is the one that you do need to know because it's outlined in red. So we're going to differentiate this to end up with that and lose the minus sign, which we'll talk about to do with Lenz's law. So in terms of what you need to know, this is the only equation that you do actually need to know. And what I've tried to show you is that this equation comes from the fact that the flux linkage looks like this, and the gradient of this is the rate of change of flux linkage, which gives us this graph, and although it should be negative, we'll deal with that now. Okay, so let's just look at the maths explanation. If we were going to differentiate the change in flux linkage per second, this is what we started off with, that n phi equals BAN cos 2 pi ft, which equals BAN cos omega t. If we differentiate that with respect to t, then the BAN omega comes outside the brackets, so the BAN omega comes out of the brackets, and we end up with the cos differentiated to minus sine. But our formula is exactly this, but the minus has gone, and the minus has gone because of Lenz's law. And remember that the direction of the induced current is such that it opposes the change that produces it. So this is why you lose the minus sign at this point. Just some quick questions, some quite simple questions. We'll do some harder exam questions in lessons, and you can find them on past papers, but these should just test if you've got an idea of some of the basic formulas. An AC generator produces an alternating EMF with a peak value of 8 volts and a frequency of 20 hertz. If you were to sketch a graph to show this, it needs to be a sine curve, because we've seen that if we integrate the flux linkage, then the EMF graph should become not a minus sign because of Lenz's law, but a plus sine curve. So you do a sine curve. The time period's 0.05 seconds because the frequency is 20, so do 1 over 20 for the time period, and the peak to peak is 16, so it's got a value of plus 8 and minus 8 on the y-axis. Okay, number 2, the coil of an AC generator has 80 turns, a length of 65 mm and a width of 380 millimeters. 38 millimeters, sorry. It spins in a magnetic field of 130 milliteslas at a frequency of 50 hertz. What is the maximum flux linkage? So we're going to use flux linkage is equal to BAN cos theta, but we know that maximum is when cos theta equals 1. So I'm just going to use flux linkage equals BAN. My BAN, B field is 130 milliteslas. The area of the coil spinning is 65 mil times 38 mil, and we know that the number of turns is 80. If you do all that, you should get an answer of 0.026, and the units for flux linkage are they are Webers, but you need to put turns on the end as well for Weber turns. Show each side of the coil moves at a speed of just less than 6 meters per second. To do this, you need to consider that the end of the coil we're interested in, if we just do a quick drawing here, the end of the coil that we're interested in is going to have a radius of half of this value of width of 38 mil, because if you imagine that it's spinning like this, so this is the motor that's spinning, there it is, then if you add half of, if this complete length here, so this length here is actually 38 millimeters, yeah, that is 38, so you would need to halve that. I don't know what's happened there, but you hopefully can see it. You need to halve that to give you a width of 19 millimeters being the radius. From that, we know that the velocity along the circumference of a circle is the total distance travelled divided by the time. The total distance is the circumference of a circle. The time is the time period. We can do 2 pi rf because frequency is 1 over the time period. So 2 pi times the radius, which I just explained is half of 38, so that's 19 millimeters, so 10 to the minus 3, and our frequency is 50. If you put all that in your calculator, you get a speed of 5.97 meters per second.